Mm. So far we know how to construct and describe the qualitative and quantitative data. We were somewhere. Yeah, so far we know how to construct and describe qualitative and quantitative data, in which we came across the tabular forms, graphs, and numbers. So we have covered the tabular forms, and I'm pretty sure that you know what I'm talking about. Then previously we learned about numbers as well. That is how to measure central tendencies, which is in front of you right now. Um, where is the pen? Yeah. So if I use the highlighter, it will be easier. So how to measure the central tendencies of the distribution, means averages and measure of spread. We have learned the measure of variation is the spread or dispersion. There is range, interquartile range, variance, standard deviation, and coefficient of variance. So you can tell me, why do we need a coefficient of variation? What's the difference between absolute and relative measure of variation, right? The absolute measure of variation gives the answer, gives the solution into the same unit except the variance, where we get the unit into square of that unit. Whereas coefficient of variance is regardless of any unit and it's given in percentage. So that's why it's really important. And we can see which is better in what attribute, right? About two different stocks or two different investment holdings. So that's why we extract coefficient of variance. We also looked into how to measure important points, that these are median, quartile, deciles, and percentile. What is the interpretation of these different important points to remove the outlier effect? So we have covered all the important points. So today we will also look at like a little bit on the skewness and how to calculate it. We also looked into the properties of arithmetic mean, which you can see just in front, and we tried to solve it through example, and also the properties of variances. So these concepts we have covered so far. So today we're gonna start the last concept of this series, of organizing and visualizing variables, and that is the left parts. So what we didn't cover so far is the box plot. Right, so today we will talk about the box plot or box and whisker plot. Um, we have already talked about the dot plot. So this is the box and whisker plot. So I'm gonna use the board and this one. That's why I already sent you the PDF file of today's lecture, so that you can, if when I will use the whiteboard, you can see the PDF files on your computer or in your mobile phones. So we're gonna cover the box and whisker plot. What is it? How do we draw it? And what's its relevance? Let's see. So for box and whisker plot, it basically shows us about different. If you can see the whiteboard, so this is like the upper part. This one, I'm gonna explain that how it works and how we draw it. We don't need to get like something new. All these concepts we are familiar with, right? you know Q1, Q2, Q3, IQR. Maybe this is the new concept for you, which is like the lower whisker or lower point, and this is the upper point. So these five things we should know. One, two, three, four, five. These five things you should know. You can also call it minimum value in the data, and this is the maximum value in the data. So it's basically it's a distribution, right? So and then we will see that how we can what we can see if we implement it through an example. So let's start from the whiteboard. I'm gonna show you the camera. So I hope you can see. You may not see. You may not see my face, but you can see the whiteboard in a good way and some invisible hand. Only a hand gonna teach you. Okay, so don't worry. So what is the whisker box or box whisker plot? It's really a simple thing. We need five things, as you can see from the slides in front of you, but I'm gonna here draw it. This is a box. This is we call it lower whisker. This is we call it upper whisker. This is about the graph representation of the quantitative data. So we missed at that point. We didn't touch this one because you need to know all the concept before that. So we need to draw lower whisker and this is upper whisker. If I write it in a clear way, whisker is the name, right? I'm sure you can read it properly. Now, which area is this? This you can call it Q1. This you can call it Q3. So it means this is 50% area of the whole distribution. So this can be distribution. We don't know the shape. It can be symmetrical. It can be skewed, means positive. It can be negative. We don't know. But what is this? The lower whisker. Um, I'm just putting so that you can understand this. So if this is Q1, it means 25% data. You can also call it 25 percentile is below this point and 75 percentile is above this point. And this is Q2, which in if it is symmetrical, then this is the shape in the middle, right? So Q2 is also median. So we know these five concepts. We should know the lower whisker, Q1, Q2, Q3, and upper whisker. So we need these points. What is the value of the lower whisker? Simple. Q1 minus 1.5 IQR. This is IQR, right? Interquartile range. Why 1.5 here? I will tell you exactly what is the interpretation of why 1.5 here. And this side is minus the quartile range, 1.5 of the quartile range of this thing. This one should be plus. So Q upper whisker should be Q3 plus 1.5 IQR. So these three things you need to draw the whisker box plot or box plot. You can also call it box plot. Why? Now it's easy. You know you can extract Q1. What is the Q1? The first quartile. You know Q2. You can extract. You can get Q3. You have already know how to get these kind of the value for these Q1, Q2, Q3, and this IQR. So based on these five values, we can plot the box. Hence, it is also called 5-number summary plot. 5 numbers summary plot. Now, it's really interesting. And it includes the minimum value. This is also known as the minimum value. And this is known as maximum value. So it's also another way to interpret or to denote to give a notation to a box whisker plot. Of course, the minimum value is like the lower whisker, and the maximum value is the upper whisker. And you know how to calculate these values. So we can draw now what information this box tells us. This box can tell us the information about the distribution, but it is different. It is a bit different than the histogram. You can tell the data is symmetry depends on the Q position of Q2. So right now it is a symmetrical because Q2 is in the middle of the interquartile. If the median is somewhere here, yeah, this is Q2. That's it. If this is Q2, then it's on the right side, so it's gonna be positive skewed. So if Q2 is on this side, more on this side, then it is negatively skewed or right skewed. So it depends on the Q2, where if Q2 is near to Q1, right, then it's positive skewed or right side skewed, and if it's near to Q3, the more it goes, the more negatively skewed it is. So one thing, it can tell us the distribution of the data. Understand? Second, it identifies the outlier, because outlier must be here in this range, out from Q1 to lower. We have already learned this concept, that why do we need IQR, interquartile range? Because to identify the outlier, if there is any outlier. So data point crosses the lower whisker or upper whisker, we can call that the outlier. So any data point which is here, somewhere here, that's an outlier. So we need to skip that. Why 1.5? Because it assists us, it gives us the minimum margin to identify the outlier. We have done like the example of students. So some students getting 100 on the upper whisker part, it doesn't mean that student is like it means that student is genius among the rest of the class. So if we include that genius in the class, it can change the distribution of the whole class, and which can be biased. So that's why we need to exclude that genius. And at the same time, if there's like some really dumb in the class, so we can also need to dump that student. So second, it shows us the outlier positions. Third, so it can show us first the shape. Second, outlier, if there is any. Third, it shows the variation of the data. We know from the width of the IQR box. So this is IQR box, right? This one in between. This total is whisker box plot. This one inside, this is IQR box. So it depends how wide is this box. If it is wider, it shows more variation. So let's say if it's like up to here, This is the box. So it means this one has more variation. And if it goes close, the more close to Q2, it will have less variation. Uh, and we know that uh, the interpretation, right? So now let's see this with an example. So I will take you back to the, so you have understood this one, right? The concept. So I will take you back right now to the shared screen, and I will move a little bit here so that you can learn from the example. So let's share the screen now. And where is the pen now? So now you understood that what is this diagram, right? If you have any question, you can ask now or later on. I will see after telling this example on the messages. Now, let's say we have gender distribution, right, of men and women. And this is the cholesterol level in men and women. So we need to define uh, means which one has more cholesterol level from the graph. So we can say on average the level of cholesterol from this, looking at this graph, we can say on average the level of cholesterol is more in male. Why? Depends. See, it's the box width, right? This box width is more in male, and the variation in the cholesterol is higher in male because this IQR box width is more, right? And it's positively skewed. So the distribution of the male should be like this, right? With this one as Q2, if I take it right. So it is positive and the male has more cholesterol level and there are no outliers. So we can suggest that according to this information, male has higher cholesterol level than female. The advantage of this, our histogram, that it consider two variables at the same point, whereas histogram shows only about the one variable. So if you consider the woman, so this will be the lower, so this will be the lower for the lower whisker for the woman cholesterol level. This will be the upper. This is the same Q1. This is the Q3. This is Q2. So you see here the Q2 is more towards the Q1 and the width of IQR is less than the width of IQR of male. So that's how we can, from the lower visceral plot, we have all the information, we just plot it, right? Let's say this one is 500, this one is 200 something. So it appears that male generally have higher cholesterol level than female. So basic thing is to how to interpret it. So you can interpret it now. So you have data x1, x2, 1, 2, x1 and y x2. This is for male and female. You can easily get Q1, Q2, Q3. You can calculate IQR. Just put it, make a table, make a graph, make a plot, and then see what does it interpret. So, do you understand this thing? Good. So now you can see the camera again. Yeah. So this topic is clear. So now you can draw the whisker box. How, before going forward, you must know how to interpret the standard deviation, right? That we know how to interpret variance, right? But how exactly to interpret standard deviation? Why? Because it's really important to know. We know how to calculate it, but what is the exact interpretation? So when interpret, you can see, right? Let me make it bigger. Now you can see properly. So when interpreting standard deviation, it means how much variation. Remember that it's the measure of the typical amount of the deviation from the mean. So if we have this data set, and let's say this is the distribution, symmetric distribution, right? And this is the mean, which we also called X bar, and there are different points like 2, 4, 3, and then this is 4, and this is 5, this is 6. So these are different data values, and on the other side we have frequency. So if this is the X bar, so what is the interpretation of sigma or standard deviation? If this dispersion is more, it's higher, it means this standard deviation is higher. If it goes closer to the mean, this means there is less variation. So if we see at the plot that this is the plot, and this is only 4. So it means there are entry values 4, 4, 4, 4, 4. So against every frequency, the X is 4. So in this case, the standard deviation or sigma is 0. Do you understand this? In this case, it is 0 because there is like no error. It's only on one bar, this one bar graph. So here we have different, if we draw a histo, right? So we have different. So the more it is spread, the more the symmetry spread, the bigger the variation will be, the bigger the standard deviation is. From here, we can use this sigma and this so what is like the difference of the how much spread it is, how much data comes under the curve, in what range, we will see in empirical rule. So there are two basic rules. So let me take you back. Um, so you see the same example here, which I just draw on the board. So it so you see it's an amount an entry deviates from the mean. The more the entries are spread out, the greater the standard deviation is. So if it goes in this way, this will increase. If it goes in towards the mean, this will decrease. Right? And similarly, this I already have shown you. Now let's see practical significance of standard deviation. If the standard deviation of the data is small, the observations are centered near the mean. We already learned that. Whereas larger deviation indicates that the data value are scattered. This idea is expressed more formally by empirical rule and Chebyshev's theorem. So these are two rules, are two ways to find out the distribution of the data, that how much data under certain um, certain curve. So let's say first, let me tell you, if your data is symmetric in this sense, right? If your data is symmetric, then we need to calculate, you need to know that x bar plus minus 1 standard deviation. This is empirical rule I'm talking about. Chebyshev's theorem we will talk later on. So 1 time SD. So this range gives us the 68% data. That's given always. So that's why it's really important to calculate the sigma and x bar. So it means 68%. So let's say we call it x bar as mu and standard deviation as sigma. So I can write in this way. So let's say this is mu, and okay, my handwriting is really poor. Yeah. So let's say this is symmetry, right? We always need to know that this is symmetry. So this we can say x bar, which is mean, or we can also denote with mu. So the spread here is, this one is minus sigma, this one is plus sigma. So we will calculate, we will say that if it's a symmetrical shape, 68% data lies under this situation. So this is 68% data. And the rest of 32% lies on each equal half. So it means 16% data is here, lying here, and 16% data lying here if we have this condition. Second, that's also known as confidence interval, that our 68% data lies in a confidence interval. So we can confidently tell about our data points. And hence, we also can calculate that if it's 2 sigma, then it shows 95%. So if our spread is among minus 2 sigma and plus 2 sigma, so it means now 98% data lies in this range, 95%. So it means 5% lying on the both side, so which is symmetric. We will solve it through example, so don't worry. So 2.5% here, 2.5% here. Why? Because overall the area under the curve is 1. So this is, you need to know that these are the ways we define the data. And say mu plus minus 3 sigma, you know, standard deviation means variation. So you can also use, I'm using standard deviation. I'm just not giving this notation to the standard deviation, which is common. So if there is a variation of 3 sigma, then it shows the 99.7% of the data lies under. Let's draw it more clearly. This is mu, which is x bar. So this is sigma. This is sigma minus sigma. This is minus 2 sigma. This is minus 3 sigma. Why? Again, you can easily get the outlier. This is 3 sigma. So here, 68% data. Until this range, 95% data lies under this range. and under this range 99.7%. So the bigger the spread, the more data comes under it. So remember, this rule is true only if it is symmetrical. If it's not symmetrical, then we have to see the Chebyshev's theorem, that how to calculate different ranges. Now let's see it through example. I can draw multiple conclusions from this. For example, take the height. Okay, so if you see the screen, you will know what I'm talking about. So I already explained this diagram to you, right? So that's exactly how the data is interpreted in different ways. Let's take example. Now the mean value of homes on the street is 125. So mu is given with a standard deviation of $35, $5,000. This is sigma, and the data set has a bell-shaped distribution, which means it's symmetry. Estimate the percentage of homes between $120 and $130. So he's saying that how many homes comes under this range on the street. So on this street, how many homes are there which cost between $120 and $130,000? So we have mu, we have sigma. Just find the distribution. So this is the distribution overall, right? So mean is 125. It is given if it is defined, and then we can see this is the 5%, $5,000 deviation from mean on every point. So this one 5 means 130, 135, 140, 145, and so on the backside. It's like this. So that's how we can draw the distribution. You can easily draw if you have these things given. So we already know that mu plus minus sigma contains 68% of the information. So if we say 125 plus minus 125 plus minus sigma is 5, which means 120 and 130. So 68%, which is this range, right? It's given. So 68% of the houses have the value between. So on this street, 68% of the houses are having a value of this. So that's how we interpret it. Understand? Easy. So have a look on this. It's not that difficult. So you see how. So that's how we interpret when it's given. Now let's take another example. Uh, so this example you understood, right? So you can practice it at home. Now there are some couple of more questions. So if the distribution of the heights of adult men is approximate a Mount Bell, which has like less spread, which means 69 with mean 69. Oops, why it is like this? So we can do like this. So it means 69 is mean. So it is mu, which is here, inches, and standard deviation is 2.5 inches sigma. So now you can calculate three things: mu plus minus sigma, which is the range of 69 plus minus 2.5. So one will give us how much? 66.5 and 71.5. So 66.5 the range and 71.5. That's the one range, right? And hence second range will be mu plus minus 2 sigma, which is 2 times 2.5 is 5. And so can I say that the range is 64 and 74? Yes, I can say it, right? After solving it. And 3 sigma means, so 95% data lies under this range, 68% data lies under this range, and 99.7% data lies under mu plus minus 3 sigma. Which is 3 into 2.5. How much? 7.5? 2.5? What is 3 times 2.5? You can calculate it, right? But probably it's 7.5. So you can say 69 plus minus 7.5, which gives you 61.5 plus minus, oh, sorry, and 76.5. So these are different data ranges I have calculated by using the same formula because mu and sigma is given. So he's asking about what percent of men are taller than 74%. So this data comes 68%. So they are not taller, they are shorter because here the range is 71. So here the range is 74. So this it means 95% data, 95% of the people, men, are having a height between 64 and 74. Now he's talking about if this is the distribution. So he's saying that this is mean and this is mu plus 2 plus minus 2 sigma. This is mu plus 2 sigma. So this one is 64 and this one is 74. So it's mean taller than 74 must lie here. So if this is 95%, so it's mean remaining this one together is 5%. So on this side it's 2.5, on this side it's 2.5. So I can say that 2.5% data, 2.5% of men are having a height more than 74 per inches. Understand? Do you understand? Okay, good. If you understand, good. Because this portion is 95%, so that's why don't consider it as a 5% portion. Don't consider it as a 5%. So this one is plus minus 2. So together, this one and this one gives us rest of the 5%. So it means 2.5% on the left tail and 2.5% on the. So if 74 here, so taller are 2.5% of the data sets, right? Rest of the examples you can practice by yourself. I have given you the slides. It's really easy, not that difficult. Just right now, tell me quickly, between what height do the middle 95% of men fall? Can you tell me this one? If you have a paper and pen, just draw the graph and see. between what height do the middle 95% of men fall? Oh, I have given the answer. You can see the solution. So of course, we have already calculated the 95%, right? Well, that's not smart to ask you this question when the answer is given. All right. So anyway, you can solve it easily because you already know that 64 to 74 we already have calculated here, right here. Right? So about what percent of men are shorter than 66.5? Now 66.5 is here. So shorter means they lie here. They lie less than here. So 50% to 34% is 16%, right? You can minus 50% because this between Q1 and Q3, you know there is a 50% data. So you take out the 34 means 66.5 plus 66 plus 34 is 60. So 16% data people lie below this one. Or if this is 66%, then remaining is 32 and 32. Half of 32 means 16% here, 16% here. So 16%, easy. About what percent of men have height between 66.7? You already know it's 81.5%. So that's how you can calculate it at home. Today you can practice. It's really fun. You can ask your fellow student that, can you tell me about this, and find out this one, right? Now we're gonna talk about Chebyshev's theorem after the break. Okay, let me see. Yeah, I think we will. Yeah, it's not a big deal. So we will finish what we have in mind today. So now you have a 10 minutes break. Enjoy the break. Talk something else other than statistics and other than this. So now you know how to use the empirical rule. So this is known as empirical rule. Remember, in empirical rule, the distribution must be symmetrical. Okay, the width can be lower or higher, but it should be symmetrical. Next, when we don't know the shape, or when it's not symmetrical, when it's skewed, then what kind we use Chebyshev's theorem, and we're gonna talk about this after the break.